application here. Now, once again, this is not how real um, liquids flow. This is just really just for us to kind of help us understand linear systems and parameters and stuff. So have some kind of a pipe system. So say you've got a pipe running in here, gets to here, maybe it splits off, gets to here, goes to here, goes to here. Say these go together to here, and this goes to here, and suppose that joins up there, and then you've got another flow out, something like this. Now I can put directions on them, but in theory they can actually flow both way, I think, in the way I'm doing it. So what we're going to have, this would be the same, as the other one. So now actually you do have to give directions, don't you? Now the directions we started out, because if you have a negative flow, then that's okay. So if you put arrows in and you say you call that x1 for argument's sake, well, actually I'm going to call this, we'll call it x1. If it turns out that you get a negative x1 solution, then that could be a flow out. But anyway, so that goes like that, that goes like that, that goes like that, that goes like that, like that, like that, like that, and say like that. Now what we're going to have different here is that at each of the junctions, we're going to have that, I better put some labels down. So say x2 is the flow here, x3, x4, x5, x6. You imagine this is water or something flowing. x9, nine unknowns here in this picture. And then what I'm going to have is that at each of the junctions, we're going to have a certain amount of the liquid actually being used. Now, I'm just going to write them like, oh, that's the use there. But really what you're thinking about is it's just a flow out of the system. But I'm going to say, oh, there's U2 being used there, U3 being used there, U4 being used there, U5 being used there, U6 being used there. But as I said, in terms of writing down the equations, a use of liquid is just a flow out of the system. Okay, and apart from that, it's pretty much the same. Flow into the system equals the flow out plus the total use. Or, well, I mean, if you consider, so here this is saying that flow out is associated with use. Yeah, so in a junction, the flow in is equal to the total flow out plus the use. So we're just considering the use really as a flow out. Okay, now the fluid would be out. Yeah. Right. So it's pretty much the same after that. So let's see an example here. I just have to, if I use particular labels. Yeah, I'm not using any particular labels. I think, okay, so we're going to identify the variables. We are going to write down linear system governing the flow, and then we're going to solve the linear system, right? So, so just taken from the question, it appears that we have 300 flowing into the system. 25 is used at A. 50 is used at B. 100 is used at C. And then 25 is used at D. Now, in fact, you could let the flow out be a variable as well. And it will come out in the wash what it is. But if you look at it, there's 300 going in, there's 200 being used, so there's 100 exiting. So that if that isn't in the question, the flow out can just be another variable, or else you can just do a single equation that the total flow in must equal the total flow out, and you can find it like that. Or else you can actually just keep doing flow in equals flow out. So I suppose also that we have 300 entering the system today and 100 leaving. Yeah, so I'm saying that information actually didn't have to be given. So I'm going to write down names of variables now. Say this flow is x1, this flow is x2, this flow is x3, this flow is x4, this is x5. So if it didn't tell you it's 100, you would just let this be x6 and it would come out in the wash. Okay, so let's highlight our little junctions. We've got a junction at A, junction B, junction C, junction D. So 4 equations in 5 unknowns. Now there's either going to be no solutions, and if there are solutions, when you've got more variables than equations, you're going to have infinitely many solutions. There's not enough information to specify the flows exactly. So we'll do junction B first. I'm just I'll look ahead so I have the right space. Yeah, so we're just going to write the equations down here. There seems to be loads of space here. So junction B gives the following equation. What flows into B? I only see x1. What flows out of B? So there's x3 plus x4, but also 50. 50 is being used. And you want to get variables equals to constant. So take away the x3 and the x4 from both sides. So x1 minus x3 minus x4 is equal to 50. Right. Now let's have a look at junction A. What is the flow into junction A? I see 300. What is the flow out of A? I see x1, I see x2, and I see 25 is being used. So I want to get the variables equal to the constant. So if I take away the 25 from both sides and then write the equality the other way around, I get x1 plus x2 is equal to 275. Okay. And then D, what goes in, I would say x4 plus x5. What goes out, I see 100 goes out, but also the 25 that is used there at D. So therefore, x4 plus x5 is equal to 125. And finally, we have junction C, which says what goes into C, I see x2 plus x3. And what comes out of C, I see x5 plus 100. And again, get all the variables on one side. So that's x2 plus x3 minus x5 is equal to 100. And I'm going to pause the video for a second and just write down those equations for myself. So now on the next page, I'm going to put these into augmented form. I'm just going to put them into that order as they appear. Okay, I think there's looking for the space. Yeah, there's a lot of space there. Okay. So note there are 5 variables, only 4 equations, so there will be at least parameter if there are solutions. So the first equation says 1x1, 0x2, minus 1x3, minus 1x4, 0x5, equal to 50. The second row reads 1x1 plus 1x2, 0x3, 0x4, 0x5 equal to 275. The next row reads 0x2, 0x1, 0x2, 0x3, 1x4, 1x5, and 125. And then the final row is 0x1, 1x2, 1x3, and minus 1x5 equal to 100. So remember what we're going for. We want to get, well, we have a pivot, that's great. And we'll use that pivot to kill that. Okay, so we're going to do row 2 is sent to row 2 minus row 1. I'm not sure how much space we need, but I think I can fit it here. 1, 0, minus 1, minus 1, 0, 50. And then row 2 minus row 1. So 1 minus 1 is 0, 1 minus 0 is 1, 0 minus minus 1 is 1, 0 minus minus 1 is 1, 0 minus 0 is 0, and 275 minus 50 is 225. Now, what we could be a bit smart here, because, I mean, we could keep on writing, and that's normally what I would do, because I have the 1s and I have the 0s underneath, but now I actually have a pivot here. I could actually attack this. Now, if you want, you can just complete this frame out, but I think actually it'll make sense here to do that. So row 3 is fine, 0, 0, 0, 1, 1, 1, 2, 5, but I'm going to go after row 4. So I'm going to do row 4 sent to itself minus the new row 2. So 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 1 is minus 1, minus 1 minus 0 is minus 1, and 100 minus 225 is minus 125. And now you might notice something. Okay. So we'll pause here for a second and just notice you have the two pivots. And now you've got two zeros here, so that's fine. So this is a pivot, and you just have to kill the thing underneath. So we need to kill this, and we can do it by adding row 3. So we save the frame here, it looks like. So, sorry, now just look where I go. So row 4. So we want to kill this minus 1. So I'm going to add row 3. So row 4 is sent to row 4 plus row 3. 1, 0, minus 1, minus 1, 0, 50. 0, 1, 1, 1, 0, 225. 0, 0, 0, 1, 1, 125. And now add row 4 sent to row 4 plus row 3. And you'll notice that they're so 0 plus 0, 0, 0 plus 0, 0, 0 plus 0, 0, minus 1 plus 1 is 0, minus 1 plus 1 is 0, minus 125 plus 125 is 0. So you end up, you get to your reduced form. Pivot, 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 reduced form, you get the staircase. Okay, so there are definitely solutions here because you don't have 0, 0, 0, 0, non-zero, so we might just note that. Also, would you, if you find me keep pressing the colors is actually disrupting, is ruining the videos, you might just drop me an email, and if totally necessary, we can actually go back to using the paper. Solutions, yes. But we have parameters. We have two columns, this one and this one, corresponding to x3 and x5 that have no pivots. They don't have a pivot in them, only x1, x2 and x4 have pivots. So take x5 to be t and take x3 to be s. Now we're going to work from the bottom. We have x5, we're going to find x4, then we're going to find, we know x3, we're going to find x2, and then we're going to find x1, and then we'll maybe have a look at the actual pipe network and see how it all looks. So looking at the second last row, that reads x4 plus x5 is equal to 125. We know that x5 is equal to t, so if I take away that t from both sides, x4 is equal to 125 minus t. Okay. Then if I look at the next row up, that's the second row. The pivot is in x2, so that's finding us x2. So it says x2 plus x3 plus x4 is equal to 225, excuse me. So x2 is equal to 225. Take away x3, which is s, and take away x4, careful with signs, is 125 minus t. So we find that x2 is 225 minus 125, that's 100. And we have a minus s and a minus minus t, which is a plus t. And then finally, we're going to find x1. x1 minus x3 minus x4. So I'm just reading off the first row is equal to 50. Therefore, x1 is equal to 50 plus x3, which is s, minus x4, which is 125 minus t. That's okay. No, I need to add, sorry. So add the x3 to both sides. That's good. And add the x4 to both sides, not take away. And this is equal to 50 plus 125 is 175 plus s minus t. So I think I can zoom out here, and if I have the pipe network up the top, I don't. So I'm just going to pause for a moment and write down the solutions. Well, I'll write down the solution altogether for us here. So we have x1 is equal to 175 plus s minus t. x2 is equal to 100 minus s plus t. x3 can take on any value, so it's a parameter s. x4 is equal to 125 minus t, and x5 as a parameter can take on any value. So I'm just going to pause the video and write those down. Okay, so I've written those down, and we're going to go back and look at the pipe network now. It was a bit messy, we'll go on this one. So we have 300 coming in. It's diminished by 25, so there's going to be 175 between, okay, this isn't going to work because I need to label the thing, so apologies. So this was the labeling. So you see, the thing is, if you label it differently, different things could be the parameter. In fact, in this one, I think anything can be a parameter. Well, I think you can't have x1 and x2 being parameters, but apart from that, I don't think you can have x4 and x5, but other than that, you can have any pair whatsoever. So if you label it differently, you get different solutions. So let's zoom in on this thing. So we found, I'll just write down the solutions beside them. So this came out to be 175 plus s minus t. x2 was 100 minus s plus t. x3 was s. x4 was 125 minus t. x5 was t. I think we said there was 100 leaving here. Then there's 25 being used here. That's all in the question. 100 is being used here. And finally at B, there's 50 being used. And if you look at this, this will make sense. So you've got 300 coming into A. 25 is used, so there's only 275. Now 175 of that goes to the left and 100 goes right. And then what goes on the left is enough water, the S here, to capture the bit going between B and C. And then there's a little bit, the water that is eventually going from C to T essentially goes down here. Okay. And then what happens is, so you got the 175, the 50 is used, so there's 125. So the 125 goes with x4, the S goes down to C, and the slack of minus T is still kept. Now I'm looking at C, so the slack of S in x2 is caught up with, so that's gone. The T is still there to go to from C to D, and then the 100 is all used up. So you're just left with the T here. And then, so you've got T here and a slack of T in x4, so that's captured up. And then there's 125 and the 25 is used up and there's 100 coming out. And I'm saying it's kind of tricky to analyze that without doing linear systems. Now I'd also say that's not a real analysis of a real problem, but it kind of helps you understand the linear systems and the parameters when you come looking at, say, structures. I think we have one more example in this. Yeah, I think this is the final example here. Yeah, happy days. So consider the following irrigation system. Water from the reservoir is pumped to town A at a rate of 100 units per hour and flows through the system eventually into the sea. Assume that water use is negligible. So here's nothing actually being used. So it's like a traffic flow on. Town A, there is a non-adjustable device pumping 30 units from A to C. At town B, there's a device which can pump a variable amount of water from B to C in case C needs more water. Assume that the flows are one way, so that all the F's are positive, and the equations governing the system are like this. So if you look at the first one, it comes from junction A, 100 in, 30 plus F1 out. Then junction B, where, no, this is junction C. So you get 30 in and F4 and F2 comes out. The second last one then is junction B. We have F1 in, F3 plus F4 out, and finally F3 and F2 combine at junction D to give you the 100 out. And what principle is used to derive these equations? Simple. Flow in equals flow out. Handy. So then the next question says, when these equations are put in augmented matrix form, with the equations, the coefficients of Fi in the ith column, and the Gaussian elimination algorithm applied, the reduced form of the linear system is given by this. Okay, so this is kind of handy because this it puts the equations in the right form, solves them, and it kind of sets it all up for you. So this is an easy one. So we just analyze it. Oh yeah, that's the flow in equals the flow out. The flow into the junction. Yeah, okay. So let's look at the pivots. Now we know it's in reduced form because the question says it is, but let's just see the staircase. There it is. And the pivotless column, which is this one, can be a parameter. F4 can be the parameter. And that's nice in terms of the problem because it's like you understand that this is the variable flow. This was the pump that could take on different values. And then it's kind of easy to solve the rest of it then. So choose F4 to be the parameter, and then we'll solve for the rest of them. So F3 plus F4 equals 70. So F3 is equal to 70 minus F4, which is T. And then similarly, F2 minus F4 equals 30. So F2 is equal to 30 plus F4, which is T. And then finally, F1 equals 70. Now that probably falls out in the wash if we just look at it. Yeah, if there's 30 there, then F1 clearly has to be 70. This is 70, this is T. This becomes 30 plus T. This becomes 70 minus T, I think, hopefully. Yeah, and we get the solution set there. I think there's one more question on this. If the flow into town C exceeds 80, it will flood. Find the possible values of T if it is flooding. So let's find the flow into town C. So town C, it's 30 plus T. So let me slow down there. So the flow into town C is 30 plus T, yeah? And then it says if that is bigger than 80, it floods. So we want to solve, here it is, 30 plus T to be bigger than 80. And with an inequality, you can take away from both sides, take away the 30 to get T is bigger than 50. There we go.